Alright, so in this one we're going to start looking at capacitors, and so far when we've talked about capacitors, we've dealt with capacitors that have air in between the two plates of your capacitor. We're going to look at in this lesson is what if you put some other non-conducting substance in between those two plates instead of air, and what happens to the capacitance and the electric field in there, and how do we begin to calculate some of those things. And so we call this type of substances, we call it a dielectric. And effectively what you do is you increase the capacitance of the capacitor by filling the space between the metal plates with some other type of material. And there are really two different types of materials we could put in there, and that's what these two different sets of diagrams get at. One would be some sort of polar material. Something like water would be a great example. What you end up doing with a polar substance is it has a positively charged end and a negatively charged end. And so when you put the electric field through it, the positively charged ends all point toward the positive end, and the negatively charged ends all point toward the positive charged ends all point in the direction of the magnetic field away from the positive plate, and the negative all point away from the negative plate. Now it's worth pointing out in a polar material you don't get perfect alignment, but you basically align the molecules in the direction of the electric field. Now in a nonpolar substance, the molecules or particles in that substance do not have a natural polarity. The electrons are equally distributed in them. So initially, it just looks like, well, just a bunch of stuff. When you apply a magnetic field, what that does to the particles is it induces a dipole in those particles when you apply this electric field. It causes negative charges to kind of pile up on the side closest to the positive end, and positive charges to pile up on the side closest to the negative end. What this ultimately does is if we have an electric field which is going this way initially, that's created by the two plates, there's an electric field created by the dielectric which is in the opposite direction. And depending upon how good that dielectric is, well, being a dielectric, that would basically determine how big this electric field is. So the net electric field actually decreases inside of a capacitor. What that means is if you hold a Q or charge constant, the potential difference decreases. And so that would mean that the overall capacitance, if you wanted to get it up to a certain voltage, the overall capacitance actually increases. So mathematically how we describe this increase is we define what we call the dielectric constant. It's given this Greek letter kappa, which is kind of a funny looking K. And we usually say that 1 is a vacuum. Now it's worth pointing out that air is really, really close to 1. For all purposes, 1.00054 is 1, unless we have some really precise measurements in our capacitor. We see there's a wide range of other values, from polystyrene, 2.5, up to water, about 80, up to even things like this ceramic stuff and strontium titanate, which are in the hundreds and hundreds of this dielectric constant. The way we define this dielectric constant is if you had a capacitor without the dielectric, C0, the capacitance with the dielectric is kappa times C0. It's basically the ratio by which you increase the capacitance by adding the dielectric. So if we rearranged our capacitance formula, it would look like this here. If we looked at the electric field of an isolated particle inside of a dielectric, it would actually be this electric field. And so if we actually calculate the electric field with a dielectric, the electric field inside the dielectric, or the net electric field, it is sigma, the charge density on the plates, times epsilon naught. Remember, by Gauss's law, that's the electric field caused by a plate of charge, divided by this dielectric constant. So if you put something with a dielectric constant of 3 inside of here, you cut the electric field by 1/3 and you triple the capacitance. So let's do a couple of quick problems. Here we have a parallel plate capacitor with a capacitance of 13.5 picofarads charged by a battery with potential difference of 12.5 volts. Charging battery is disconnected and a slab of porcelain, which it says has a dielectric constant of 6.5, is slipped between the plates. And it wants to know what is the potential energy of the capacitor both before and after the slab is inserted. So remember, the potential energy is 1/2 CV squared. So we can actually calculate the initial potential energy of the capacitor, which is, well, 1060 picojoules, or times 10 to the negative 12th. We could also say 1.055 nanojoules, I guess, if you wanted to. Now what we can do is we can figure out the charge that's stored on the capacitor, because guess what? The charge will remain constant in this case. So if we plug that in, or we could actually say, oh, we know how charge and capacitance relate to one another. I know how the capacitance is going to change. It's going to change by a factor of kappa. And so what's going to happen is we divide our initial potential energy by the dielectric constant. So the energy stored in the capacitor decreased as well, 162 picofarads, which makes sense because, well, the capacitance decreased, or the capacitance increased. So you might say, or excuse me, it should be picojoules. I'm not sure why I got that unit wrong in there, but I did. Now you might say, what happened to the other 80 picojoules, or about 80% of the energy? Well, if you were to actually slide the plate in there, you'd find that the plate actually gets pulled into the capacitor. It's actually kind of cool. So let's look at Gauss's law and look at how it plays a role in dielectrics. And here's the way we did our capacitor initially with this Gaussian surface. The blue one is positively charged. I said the charge enclosed is Q. The area, really it's A here, which is equal to the area of the plate. And so we could calculate the electric field by doing Q divided by area over epsilon naught. Now it's worth pointing out Q over area is really charge density. Now if we're doing a dielectric, we need to remember that a charge of negative Q builds up on the inside of this yellow sheet here. Now negative Q may not be the same size as Q, that's why I've called it negative Q prime. So total charge enclosed is Q minus Q prime, and so I could say the electric field is Q minus Q prime divided by A epsilon 0. Now if we say that this statement is true, that the electric field decreases by a factor of kappa, we can actually look at how the charge decreases, that the difference in the charge is equal to charge divided by kappa. And so we can rewrite Gauss's law adding the kappa in here. And so this would be Gauss's law inside of any type of dielectric material. And this would kind of be in general. If you put a charge inside of, let's say, plastic, and you wanted to figure out what the electric field caused by that charge is, it would actually probably more accurately look like this than Gauss's law. So let's do kind of our last problem here. We have a parallel plate capacitor with two plates. The area of the plates I've saying is 115 centimeters squared, and they're separated by a distance d, which is 1.24 centimeters. And it's partially filled by a dielectric material with a thickness b, 0.78 centimeters. The dielectric constant of that material is 2.61. We put a voltage of 85.5 volts across the capacitor, and I want to figure out what is the capacitance of this capacitor. So I'm going to go through several steps working through this problem because it gives us some ways to kind of describe things. First of all, find the capacitance without the dielectric. Well, that's pretty easy. We could use Gauss's law to find the electric field, or I could just use the formula for a parallel plate capacitor. Plug in the values I have, I get 8.21 picofarads. Second step I'm going to do is figure out what is the charge on the capacitor plates. Well, that's pretty easy once I know the capacitance, because capacitance times voltage equals charge. So that's 702 picocoulombs. Next step, find the electric field between the two plates. I'm essentially using Gauss's law, the charge Q enclosed, the area A, and solving it out for my value. If I plug in my values, I get 6,900 volts per meter, or 6.9 kilovolts per meter. So really I've done everything making the assumption that the dielectric wasn't there. Now the next step I'm going to do is figure out what is the electric field within the dielectric, and what I'm ultimately going to do is use a Gaussian surface that looks more like Gaussian surface number 2 here. If I kind of work that out, I could say that the electric field is equal to the initial electric field divided by kappa, and so 2640 volts per meter. The next step, I'm going to find the potential difference within the dielectric, or with the dielectric, excuse me. And so the way to do that is to integrate E from the negative side to the positive side. Happens to work out that the electric fields are all in this direction. And so we'd have E0 D minus B, so that would include this area and this area, plus E times B, which would include the area of the region where we're in the dielectric. And so you get 52.3 volts, which is certainly less than the original voltage. And then find the new capacitance. So we find the new capacitance. There we go, 13.4 picofarads is the new capacitance. Now, we had to do it this way mainly because we didn't have a dielectric which completely filled the capacitor. We only had one that partially filled the capacitor. If we had one that completely filled the capacitor, it'd be easy enough just to say kappa times, kappa times A over epsilon naught D, or kappa epsilon naught A over D. That didn't really work out this time because we only had partially filled. Now, it doesn't matter in this calculation if this dielectric is in the middle, or if it's on one side or on the other side, or offset. As long as there's a dielectric with a thickness of 0.78 centimeters, this calculation would work. So that's kind of a quick overview of dielectrics and how those play a role in capacitors.